I want to move to the next topic, which is by my good friend Gianmarco de Felice. Gianmarco, it's all yours.
Thank you, Barzin. Thank you for your introduction. And my presentation is related to FRCM composites, and I will provide an overview of the tensile and bond properties of these systems, which are having a great interest in recent years due to many reasons. First of all, a lower impact and higher sustainability with respect to classical FRP systems, a much easier application, which is suitable for rehabilitation of structures, and rehabilitation of structure is getting much importance, especially in the European countries. However, there are still some constraints that have to be taken into account that are mainly related to the fact that this technology is rather new, because it's no more than about 10 years that we have research on FRCM systems, at least a systematic research on FRCM systems. And therefore, there is a need for ensuring durability and providing some research feedback on real applications. A few years ago, I would say that there is still lack in product qualification and design guidelines, but I would say that now the qualification of this system is well established. In the USA, there is the AC434 acceptance criteria that is well known. And also in the side of guideline, very recently we have the 549 document on the repair and retrofitting of concrete structures with FRCM. And very soon we will have also a guide for repair and strengthening masonry structure with FRCM systems. So both qualification and design guideline are quite well covered by existing documents, very recent existing documents. Well, I would like to say that it was not easy to draw a guideline for these systems, because these systems have a very wide range of properties. This was assessed during a large round-robin test that we carried out a few years ago within a RILEM technical committee, and this activity involved 20 research institutions from 7 European countries, and we had the possibility to test 24 strengthening systems provided by 11 suppliers, which cover most of suppliers that are active, at least in Europe. And the systems are, you can see in this slide, they are classified based on the textile that is used. And so we have aramid, basalt, carbon, glass, PBO, and steel textile. And the equivalent thickness of these systems range from 0.04 millimeters up to 0.22 millimeters, while the grid or fabric spacing ranges from 5 millimeters to 30 millimeters. So you can see here the number of different textile and also the differences in thicknesses and in spacing of this system. Coming to the mechanical properties, we can see in this slide the different tensile strength of these systems, which range from about 400 megapascal of the less resistant glass up to about 3,500 megapascal of PBO and steel fabric. However, as you can also see in this slide, because the tensile strength is represented in gray, while the bond strength is represented with a different color depending on the system. And you can see that the behavior of this system, especially for designing the strengthening with FRCM, is mainly controlled by the bond, which is generally lower than the, with respect to the tensile. And the bond, you can see here, the bond capacity range from about 300 megapascal up to 3,000 megapascal. But it's also interesting to look what's the capacity of the systems in terms of load, not in terms of stress. And if you see the load capacity, well, you have a really wide range of system of more than one order of magnitude, from 20 kilonewton per meter of capacity up to about 250 kilonewton per meter of capacity. This explains how wide is the class of FRCM systems and how difficult it is to get the mechanical properties of the system, since like all the brittle systems, you really have a very strong sensitivity to testing of these systems, because as you can see here, which is the test on PBO made by 4 different laboratories, 5 specimens of PBO per laboratory made by 4 different laboratories. You have so different values ranging from about 200 megapascal up to 2,000 megapascal up to 4,000 megapascal. And such a wide difference between testing mainly depends on how you grip the specimen. If you use hydraulic grips or not, this will change significantly the experimental results. And not only you have a wide variability depending on testing apparatus, but even with the same apparatus, you get a very large scatter in the results. As you can see here, in terms of tensile strength, the tensile strength, the characteristic tensile strength is about 79% of the average tensile strength. But in some system, as you can see here, in one carbon and one glass system, you have the characteristic value which is about 50% of the average value. And the things are even worse in terms of bone properties, because bone properties, characteristic bone, 9% of average bone strength, but in some systems, the characteristic strength is about 30% of the average bone strength. So there is a huge variability of the system and a very strong sensitivity of the system that depends also on casting and on curing of the specimen. And these should be also checked in real application, where the quality control of the real application has to be enforced to be sure on the result, on the final result of the real application. Not only it is difficult to evaluate the strength of the system, but also the displacement and the strain, because like all brittle systems, since you experience discrete cracking when testing the behavior of this system, you have to define a basis of the measurement in order to get a reliable value of the average strain. Otherwise, you will completely have wrong results. Let's come to give a view on the final behavior of this system. This is a different. This is a graph that comprises the behavior of 9 different textiles. You can see here a PBO, 2 carbon system, 2 ultra high tensile strength steel, 1 stainless steel, and 2 glasses and 1 basalt, 9 systems. And you can see that here you have a an elastic moduli that ranges from 300 gigapascal up to 50 gigapascal, 300 for PBO and about 50 for glass, and a tensile strength from 3000 megapascal, again PBO and steel, up to about 700 megapascal for glass. Things change a little bit when passing from textile to FRCM specimen, because here you have the contribution of the matrix, and this explains why you have this first branch, which is much stiffer before the matrix experience some cracking, while after cracking the behavior is quite similar to the bare textile with some tension stiffening. And things change again when passing through the bond behavior, because the bond behavior is very different from, as you can, if you look at the PBO in terms of tensile strength was about more than 400 megapascal, while the PBO bond strength is lower than 2000 megapascal. And the same happens for carbon systems and also for stainless steel systems that experience some slippage. Such different behavior when you make a bond test on this system suggests a European guideline to make use of both tests, bond and tensile test, because from the bond test you may be able to have the capacity in terms of strength, while from the tensile test you can have an estimate of a sort of equivalent modulus of elasticity and a design strain that you can consider for real application. And it's important to understand that this class of system is quite different also in terms of failure mode, because while in basalt and glass system, the failure mode is mainly controlled by the textile rupture of the fabric. In steel systems, you experience essentially a cohesive failure within the matrix, not within the substrate like in FRP, but within the matrix, while for carbon and PBO, the failure mode is essentially controlled by the slippage of the textile within the matrix. And so these different failure modes are responsible for such wide scatter of results in which you have strength ranging from 3000 megapascal up to less than 300 megapascal, and elastic moduli from 250 gigapascal up to about 40 gigapascal of elastic moduli. And if you look at the difference with FRP systems, you clearly see that the FRCM systems are lower both in terms of strength and in terms of stiffness, much lower, I would say, as you can see in this slide that represent all the FRP, carbon FRP systems that have been qualified in Italy since today, compared to the FRCM system, carbon FRCM systems that have been tested within this round robin. And well, so I hope that I provide you an overall view of the differences in FRCM systems, and I just come rapidly to outline some aspects that deserve some interest in research that are essentially related to design and to experimental testing. For what concerns the design, much effort has been devoted to evaluate the capacity, the strength capacity of members retrofitted with FRCM. Now there is a need to evaluate the displacement capacity and the change in stiffness of these members retrofitted with these systems. This is very important, especially in earthquake rehabilitation. And for what concerns the experimental activity, there is a need of looking more close at the fatigue behavior under cyclic loading. This is mainly important for application to infrastructures and durability of the systems, since the use of inorganic matrix make the system more sensitive to the exterior, to the external agents, and again, design of connectors that can really improve the effectiveness of these systems. And I finished my presentation, and I thank you very much for your attention. Thank you very much.
Thank you very much, Gianmarco. Really appreciate the overview that you provided in, in some of the challenges that we have in this area. One question that we have is, how important is the microstructure of the surface to the bond strength, to the fiber bond strength? As far as, is that one of the issues that you think should be also addressed as we're doing, these different type of system bonding characteristics, because these fibers are so different than one another?
Yeah, thank you. This is a very important point. I completely agree with you, because especially in systems like carbon and PBO that experience sliding within the matrix when subjected to bond test, a coating or impregnation of the fabric or surface treatment of the fabric is really very important. And so there is I think that most of producers are taking care of this aspect, because this coating is very important to improve the bond, and also maybe to improve durability of these systems, because with the coating you also avoid the exposure of the fibers to the external agents. So this is a really very important topic, especially I would say for carbon and PBO systems, maybe less for glass and basal systems, where you essentially the bond is usually enough within the matrix.
Yes. One other question that we have also has to do with the means of measurement of the stress of converting from the load to the stress has to be affected by the number of yarns, the size of the yarn, and the number of filaments in a yarn, and the effectiveness of the yarns within a roving that is used in there. Do you have any idea as far as how we should kind of in a way address that? Because in some of these large rovings with 2,000 or 3,000 fibers, then we really cannot use the bond strength or even the tensile stress in a well-defined manner, because some of these are not very well bonded to each other.
Yeah, completely agree also in this case, because if you use not impregnated textiles, clearly the filaments they do not have the same stress. So when we speak about strength of this system, we always speak about the average overall strength, which you measure by dividing the load by the overall section of the textile. But
yes,
the textile, since it's brittle, if all the filaments do not work in the same manner, you will have a very strong decrease in the resulting strength with respect to the effective strength of each filament. And so this is also a very interesting topic. You have to impregnate the textile, but you have to allow for workability, and this is not easy. So again, there is a challenge for producers to work in this side. Absolutely.
Okay. Thank you so much. I appreciate your answers to the questions.